I hope you wouldn't get a question quite like question 7 in your exam. This has come from a slightly older syllabus, but you never know, so let's see if you can do it. I've changed the numbers from here so that the method I'm going to use will be the same as the one for the book, but the answer will be different. So an electron is trapped in a solid between a group of atoms where the potential is 3.6 volts. The de Broglie wavelength of this electron is 1.4 nanometers. I have to remember what de Broglie wavelength means. Remember that particles sometimes behave as waves. If a particle is moving, it behaves as a wave, and the wavelength that it behaves as we call the de Broglie wavelength. And the equation we use for that wavelength, lambda equals h over mv. So I've got this electron trapped in a solid. It must be moving, so otherwise it wouldn't have any velocity, but it can't move out of the solid, it's trapped by the atoms. It's asked for the speed, so there's the formula, lambda equals h over mv. We can rearrange the formula. V equals, you can do it in 2 stages. I'm going to go straight to do it in 1 stage. I'm going to take the V across to the left, I'm going to bring the lambda to the right. V equals h over m times lambda. And then I need the values. I could look them up. Planck constant 6.63 times 10 to the minus 34. M, what's M? It's the mass of something. Mass of what? Mass of an electron. Look it up. 9.11 times 10 to the minus 31 kilograms. Lambda is the wavelength, this de Broglie wavelength. 1.4, but remember, it's nanometers. That's times 10 to the minus 9. So get my calculator out, and I get an answer of 5.2 times 10 to the 5 meters per second. It's worth doing a common sense check on that. 5.2 times 10 to the 5, so 500,000 meters per second. Is it fast? Well, yeah, it is blooming fast, but it's nowhere near the speed of light. We know that electrons are little things, they can go fast, but it's not anywhere near the speed of light, so that's quite feasibly a sensible answer. Right, next thing, kinetic energy. Remember from G to C the formula for kinetic energy? Kinetic energy is a half mv squared. It's all very straightforward. We know the mass, you just worked out the speed, bung the numbers in. So half times the mass of the electron and we're getting 1.2 times 10 to the minus 19 joules. When we look at that answer, we spot that it's a bit less than an electron volt, and that tells us that it's probably the right sort of answer, because all the questions we deal with to do with atoms and energy levels, it's always with a few electron volts, so that's almost 1 electron volt, so chances are we're in the right sort of ballpark with that answer. Right, now part 3, this is the bit that's a bit tricky, and for this reason I don't really think this is an AS topic on the current spec, so I don't think you'd have to do it, but let's do it anyway. The sum of its kinetic energy and its potential energy. Now, how do we find its potential energy? Well, the information given in the question says that the potential at this point, because of the atoms that are around it, is 3.6 volts. And I think really it is an A2 topic to really understand about potential. But 3.6 volts, a volt means a joule per coulomb. So what this means is that at this point where the electron is, or in this region where the electron, because the electron can't be to points, it's whizzing around. So in this area where the electron is, the energy would be 3.6 joules for every coulomb. So the potential energy, it's 3.6 joules for every coulomb. How many coulombs are there in an electron? 1.6 times 10 to the minus 19. But an electron is negative. So therefore, I need to put a minus sign in the answer, and I get a minus value for potential energy. I get an answer of minus 5.8 times 10 to the minus 19 joules. And the question asks for what's the total of kinetic and potential. So the total, U total, is, well, add them up. 1.2 times 10 to the minus 19 added on to minus 5.8 times 10 to the minus 19, which is minus 4.6 times 10 to the minus 19 joules. As I say, that's a slightly tricky bit. Don't think you'd really be expected to do that. But look at this answer. We say that the total kinetic and potential energy of this electron is negative. In other words, being stuck between these atoms and whizzing around, it's got less energy than it would have if it was outside the atoms, not affected by anything. So that actually tells us that this condition is stable. The electron isn't going to try and escape. The electron isn't going to leave this place because it's got less energy staying there than it would have if it was outside. Right, part B. Calculate the energy of a photon of that wavelength. So this has got nothing to do with those electrons that we've been talking about. Just a straightforward, how do you find the energy of a photon when you know its wavelength? E equals HF, and we could work out the frequency, or we could sort of combine the formula, because we know also, and it is given in the data book, the data book does give you the form of the equation, E equals hc over lambda. So that's the one to use when you've got the wavelength. So, Planck's constant, look it up, 6.63 times 10 to the minus 34. C, of course, is the speed of light. 3.00 times 10 to the 8 metres per second, divided by the wavelength, 580, but it's nanometers, times 10 to the minus 9, 3.4 times 10 to the minus 19 joules. And then the last bit, state and explain whether or not the electron in part A can escape from the group of atoms if it absorbs this photon. Now, because I've changed the numbers from your question, I might end up with a different conclusion from you. But we saw that the total potential and kinetic energy of the electron was minus 4.6 times 10 to the minus 19 joules. The photon, if this photon comes and hits the electron and gives its energy up, the only energy it can give is 3.4 times 10 to the minus 19 joules. So is this energy enough to add on that and give 0? Obviously it isn't. So therefore, using my numbers, this photon does not have enough energy to let the electron escape from the group of atoms. Not going to bother writing that down, we've got the conclusion. You'll have to look at what values you get. And I haven't actually done the question with your values. You could come up with the same conclusion, you might come up with the opposite conclusion. All depends on how those numbers compare.